Thank you once again for being here for our tutorial. I know it's pretty early Saturday morning, so we very appreciate you being here. So for this part, I'm going to talk about the computational methods for event characterization and identification. So here is a little bit of background of me. So I had a PhD in computer science from Arizona State back in 2014, and I worked at IBM Research for a year before joining the University of Illinois at Chicago as an assistant professor. And right now, I am an assistant professor in the Information and Decision Sciences department in a business school. People often ask me, what's your feeling about working at a business school with a CS background? So this is the picture I often show to them, which is feel like working behind the enemy lines. But in the same time, I got exposure to a lot of interesting business problems, which is also one of my main research areas right now. So my current area of research is to analyze large-scale human behaviors using social media data for analyzing the public events, including the big events like the Oscars or the presidential debate, to the small-scale, less-known events such as a local event like a block party in your local neighborhood. So Yuru talked about one of my work on Huli, which is to use social media data like Twitter to build a hyper-local system for people in a local neighborhood to know better about their neighborhoods and also their neighbors. So the second line of my research is to analyze using social media to analyze the crowdfunding campaigns. So the crowdfunding campaigns such as Indiegogo and the Kickstarters are extremely popular right now. And one of my research tasks is to analyze the alignment between the social network usage and the objective of the crowdfunding campaigns. So what we have found so far is that the strong tie on social network has a very positive impact for public campaigns, and the weak tie, the weak social tie, is better for private campaigns. So the third line of my research is to analyze and extract marketing insights from social media. For example, we have done extensive work mining the customer service data on Twitter to analyze what impact or what factors affect a customer service agent on Twitter to respond to a complaint from a customer, and also what kind of factors affect the customers to be satisfied after the engagement with the customer service agent on Twitter. Okay. So today, I'm going to talk about some of my current work and also survey the state of art on these two tasks. One is to categorize the events using social media, and the other is to identify the events from the social media, which is also known as event detection or event extractions. So for the first part, I'll mainly talk about two tasks, which I think are most important tasks, as highlighted by Yuru. So the first task is to model the event dynamics, which is an essential step for event understanding and in-depth analysis. And the second one is to infer the event sentiment, the sentiment of event topics, and the sentiment of event segments that expressed through people's responses. So I want to note that the event topics themselves, they do not have their sentiment. Okay, the sentiment comes from the people. When people talking or tweeting about or posting about these topics, when they respond to or when they engage with the event, they often express their sentiments. Okay, so the sentiments comes from people, not from the event itself. So the very, very basic or the fundamental question we want to answer in this line of research, you may wonder, okay, so why do we want to do event analysis using social media? So the very basic question we want to know is what kind of insights, analysis, and other activities can be enabled through the support of automated event analysis. Right, so this is a very fundamental question we want to answer before we develop any techniques. So we want to know why we want to do this. What's the real motivation, right? So to answer these fundamental and very kind of challenge questions, what do we do? So we looked at how events are covered by the news for the indicators of the importance and newsworthiness that would inform our research. So we look at the current practice that the journalists are doing right now to inform better of the research, like what problems should we focus on, okay? And what we find through reading the newspapers and also checking the news website is that we find there is a tendency to cover the decisive moments which draw the divergent point of view, okay? So this is what they call newsworthy, like attract people's attentions. Okay, and on the other hand, according to the very classic journalism guidelines, okay, so basically these journalism guidelines tend to favor the news stories about events that were very surprising, unusual, or they are particularly good or bad. Okay, so this is basic news guidelines for the journalists to cover the events. So they want to find or extract the decisive moments of the event, and they also want to extract the sentiment of the event. Okay, so based on this, so we decided to develop techniques, or a lot of research have to decided to develop techniques to study the magnitude and the dynamics of social media responses to different topics with sentiment analysis will be on these topics will be also very useful, to extract what are particularly good or what are particularly bad. Okay. So that's the background. Okay. So in order to support this kind of analysis, extract event topics and also extract the sentiment about these event topics. So what are the main steps that we're going to do given event and its social media responses? So the very first step we need to do is first to align the event with its associated social media posts. So given event and given some kind of document about the event, such as the event transcript, and also given the social media posts about this event, the very first step we need to do is to establish the alignment between the event and tweets. We need to figure out what this tweet is talking about and what part of the event this tweet is talking about. So we need to establish the alignment first, okay? And then, given the established alignment, what we're going to do next is to realize the vision of automated event analytics. In that sense, we need to do in-depth event analytics based on the established alignment for extracting event topics as well as the sentiments about these event topics. Okay. So let's first talk about how do we establish the alignment between event and its associated tweets. So the very, very standard or popular, even simple approach is so-called time window approaches, or some people even call it fixed time window approaches, depending on the length of the window. Okay? So the basic assumption behind this approach is that it assumes the social media posts correlation with the topics of the event that occur within the time window around the post timestamps. So basically, they assume that given a time window of the event, all the tweets or all the social media posts that fall in this time window should be correlated, highly correlated with the topics of the event that appear in these time windows. Okay? And this one, it sounds very simple, right? Because you just set up the time window and you just count how many posts, how many social media posts, such as tweets, fall in this time window. Then you will assume that all these tweets within this time window should be highly correlated with the part of that event in this time window. Okay? And such simple yet very popular approaches have been applied widely in a wide range of applications. Okay, as we will see later. So I will show you one very, very classic example of the application of this time approach. This work also mentioned in Yuru's part. So this is done by David Shamar, Lyndon Kennedy, and Elizabeth Churcher on tweeting the debates to understand the community annotation of uncollected sources. Okay, so the goal or the task of this work is to investigate the practice of the sharing short messages such as tweets along the live media events. Okay, and the particular example they used in their work is they get the Twitter tweets to analyze its the usages during the 2008 presidential debates. Okay, and so the data set. So for the data set, they crawl the tweets using a specific hashtag, tweet the debate and the debate 08 in the November of 2008. So all the data here, all the tweets here are already, because they get these tweets using this specific hashtag, so all these tweets they have are relevant to the event. Okay, so all the tweets they have are relevant to events. And you may wonder, okay, so it is possible that there are also many other tweets that without these hashtags are also about the event, right? All these tweets with these hashtags may not be that relevant to the event. So this is a problem that we will discuss later, which is to extract the event from tweets. Okay, so for now we assume, given this work, we assume all the data, all the Twitter data we have are relevant to the event. Okay, and so for the events, they get the debate video from the C-SPAN found on YouTube, and they also get the closed caption data pulled from the C-SPAN. So they have all the description about events, like the transcript of the event. Okay, and then C-SPAN also has a interactive timeline of the debate. And the timestamps, which timestamps the high-level topic areas such as the opening, the financial recovery, solving financial crisis, lessons of Iraq, and so on. So basically, they also know, under their input of these studies, they also know the segment of the event. So next is so in order to use Twitter to analyze the event, also in the same time to analyze the Twitter for the event, they need, as I said, they need to establish the alignment, okay? And they use this time window-based approach. So as you can see vertically, there are a lot of dotted lines vertically, and each of them represents one of the event window, okay? And how do they establish the event window? As I said earlier, that they know the segment of the event. So they know the boundary, the segment boundary of the event. So each of this segment talks about a particular topic, such as the financial recovery, solving crisis, lessons of Iraq, and so on. So they just set up the time window and pull all the tweets that fall in this time window to be correlated with each segment here. Okay, so this is a very, very simple approach and a kind of straightforward approach. Okay, and then based on this established alignment, using this time window approach, they are able to categorize the event in depth. So one of their tasks is to categorize the event via the social graph. So they first establish the alignment, and they also get all the tweets within that time window, and they construct a social graph of Twitter users based on their mentions. And they can do some PageRank analysis to analyze which one is the most important node here, such as based on this result, like Barack Obama, the News Hour, and John McCain, they are the particular important node here, as you can expect, because the debate is between the Obama and John McCain in 2008. Okay. And what they also do is to look at the topical alignment. So we have a graph here, and above this arrow here are the topics extracted from tweets for each time windows. Okay, and in order to rank the terms or the words in the tweets, they just use a very simple TF-IDF approach to rank. And below that is the important words also ranked by TF-IDF extracted from the event transcript. And as you can see, that some of the alignment makes sense. Right? Some of the words that mentioned in Twitter are also mentioned in the debate. Okay? But many of them do not make too much sense. Like for these two segments of the event, the topics of or the top word of these segments of the event, they do not appear in its corresponding tweet for in this same time window. Okay, so which essentially shows that the time window based approach, they often do not work very well. Okay, because it relies on such a strong assumption that enforce the tweet's correlations with the event based on the time window. That's just too strong. Therefore, people developed various topical inference-based approaches to relax that assumption, to relax that strong enforcement. So I also did some work here in this space, so which I'm going to talk about later. So the basic assumption of these topical inference-based approaches is that the social media post, instead of to being enforced to the event segments, right now we assume that the social media post can respond to any topic of the event, irrespective of whether the topic has been discussed before, is being discussed now, or will be discussed later. Okay, so we relax that strong enforcement imposed by the time window by assuming that the topic of the tweet or the social media post can be correlated with any topics, regardless of the timeline. Okay, can be correlated with any topic of the event. And on the other hand, since we are modeling the topic inference, and so we will say that the topic inference has from the event on its corresponding tweet have different strengths. This is because the responses of the social media, they are generated by the audience to express their interest in the event. So they can be deeply engaged during the event, so their topic inference will be very strong, or they can be lightly engaged with the event. In that case, the topic inference from the event to the tweets will be considerably weaker. Okay? So the problem is, how do we model such topic inference from the event to the tweet, and how do we model the strength of this topic inference? Okay. So then, to solve this problem, I proposed a model called ETLDA. So the ETLDA model is a kind of a very intelligent model that it can do a lot of things in the same time. First, it can infer the topics of the event and segment the event into a sequence of segments where each of the segments talks about a particular set of topics. And in the same time, ETLDA can identify or to infer the strength of the topic inference. So it can, based on the inference, it can classify the tweets into two types, the specific tweets or the general tweets. The specific tweets, we assume that it is strongly influenced by the topics of the event. So for that type of tweets, we also infer which segment does this particular specific tweet refer to. On the other hand, we also have a general tweets where the content of this tweet is lightly or weakly influenced by the event. So we will see that later. So here is a problem definition about this event tweet alignment problems based on the topic inference. So given a event transcript S and its associated tweet T, we want to find the segment S, small s belongs to S, which is topically referred by tweet T. And the alignment requires to extract the topics of the tweet and also segment the event into topically coherent chunks. And what are the challenges in this task? As you can imagine, that the first challenge is the topics and the event topics, the tweet topics and the event segments, they are latent. Okay, so we do not have a very clear boundary of the event, topic boundary of the event, and also the event topics are unknown. On the other hand, as I said earlier, that given the topic inference, tweets are typically influenced by the content of the event, and a tweet's words topics can be very general, very high level, and which is very high level and consistent across the entire event, or they can be very specific, which is concrete and relate to the specific segments of the event. Okay, and in the third challenge is that an event is formed by a discrete sequentially ordered segments, and each of which talks about a particular set of topics. And again, these topics and segments, they are latent. Okay, as you can imagine, that there's maybe some existing approaches to solve these problems. One can imagine is one possible approach is to apply some existing event segmentation tools, such as hidden Markov-based tools to segment the event. And once we have the event segments, we can apply some topic models, such as the LDA or LSI, to model the topics, right? Because we talk about the topic inferences, we can use this approach. And then we can correlate, we can measure the distribution similarities between the topics of the event segments and the topics of the tweets to establish the alignment. Okay, so this is one of the possible approach. But we argue that this possible approach or possible baselines does not work or cannot capture the complex interactions between the event and tweets. And we argue that actually the event and tweets, they are interdependent, not as independent as this approach. So why the event and tweets, they are interdependent rather than independent? So we can imagine this. So given an event transcript, so if we look at the event transcript, can you imagine what people are talking about in their Twitter content? You can, right? So by just looking at the transcript, you can somehow guess, somehow infer the timeline of the tweets. On the other hand, if I just give you the Twitter content, I do not give you any information about the event. I just give you the Twitter content or the tweets about this event. Can you infer what people are talking about in the event? You can do that too, right? So basically, this says that the event and the tweets, they are interdependent. So how do we model these interdependencies? So we propose this ETLDA model, which essentially is an extension of well-known LDA model. So the ETLDA model has two parts. On the left-hand side, we have a LDA-like model to model the event. And on the other hand, on the right-hand side, we have a model, a graphical model to model tweets. And we have the variables to control the event segments, also to control whether a tweet is a specific tweet or a general tweet. If it is a specific tweet, then the topics or the topic distribution of these tweets is the same as the topic distribution of the segment that this tweet refers to. Okay, and on the other hand, if this topic distribution is general, meaning that this topic of the tweet is very high level and does not get influenced from the from the event topics, then the topic of this tweet is sampled from a general event distributions. And all of these are controlled by different variables, such as C of t here, which is a binary variable to determine, S of t here, which is to determine which segment that this tweet refers to. And as we all know that in these LDA-like models, we often have the parameter coupling, which implies that we have to develop approximate inference algorithms to infer the parameters of this model. What we did in this work is to use the Gibbs sampling to infer the parameters of this model using these updated rules. Okay, and to evaluate the effectiveness and efficiency of the ETLDA, we performed the ETLDA for 3 tasks. The first one is to extract the topics from the event and also from the tweets. And also, we're trying to predict the topic inference from the event on its Twitter responses. And since ETLDA can also do the event segmentation automatically, we evaluate the event segmentation performance as well. So to set up the evaluation, we obtained the tweets from the President Obama's speech on the Middle East using this specific hashtag #MeSpeech. So again, all the tweets tagged with this hashtag are relevant to this event based on our assumption. And also, we get the data from the Republican primary debate in US using Reagan debate hashtag. And we get the event transcript from New York Times. So here is a extracted topics from the Twitter and also from the event segments. And according to our qualitative evaluations, the extracted topics are much better and make sense than the time window-based approach. And here is also the performance of event segments. We compare this event segments of performance of ETLDA with LC-SEC, which essentially is a HMM-based event segmentation tools. We trained it on 15 states HMM. And after the segmentations, we asked 5 graduate students to see which extracted segment makes more sense. And in general, we find that the ETLDA performs much better, achieving the lower PK value, where the PK value essentially represents the probability of the wrongly segments. So the lower is better. Okay. So enabled by ETLDA, so ETLDA essentially established is a event alignment tool which establishes the alignment between an event and its corresponding Twitter responses. We are able to conduct some very interesting in-depth analysis about the dynamics of the event. So here is one of our study. We're trying to understand the patterns of the people's engagement with the event on Twitter. Okay, so this is a graph showing the people's engagement for the primary debate, and I segment the event based on its timeline. So the left-hand side, the blue curve is for all the tweets before the event, and the red ones are for the Twitter responses during the event, and the green one is the tweets after the event. Okay, and what we can observe is that at the very beginning we find the y-axis here is the percentage of specific tweets, meaning that they're specifically talking about the event. So at the very beginning, we can say that you can see very beginning for the blue part, most responses before the event are very tangential or about very high-level themes of the event. This makes sense because many people before the event, they do not know what the people in the event will talk about. So they can only comment on a very high-level topics of the event. So their behaviors are very high levels. And towards the opening of the event, we observe a rapid increase of the percentage of the specific tweets from 33% to 54%, because people suddenly get more detailed information about what people probably will talk about in the event, and their engagement suddenly becomes very high. And during the event, we can see a lot of fluctuations, these up and downs in this red curve, which somehow implies that the controversial topics they are mentioned and the responses they are pronounced. And also, as you can imagine, after the event, okay, the percentage of the specific tweets, they drop down very quickly. And this is kind of interesting. So we look at data to understand why. And from the inspections, we figure out that right after this primary debate, people stop talking about the very specific topics of the event. Instead, they talk about the performance of these two people who win the debate and who lost the debate. So based on our definition of topic inference, this is not specifically about the event, but rather about the overall of our event. So the percentage of the specific tweets, they went down significantly. So the insight from this graph essentially is to say that the crowd's responses tend to be general and steady before and after the event, while during the event, they are more specific and episodic. Okay. On the other hand, we conduct the second analysis to look at what's the tweeting behavior during the engaged event. So we have this graph, and this graph somehow is not straightforwardly understandable. So let me explain. So the x-axis here is the timestamp of the event. Okay, so they are ordered by the timestamp of the tweets, essentially represent the timestamps of the event. And the y-axis is a segment, the event segments. So we in this case, we segment the event into 14 chunks of 14 segments. And each dot on this graph shows a specific tweet, the reference of the specific tweets. So what's interesting about this graph is that if we look vertically, assuming that following along this red vertical line, that the event is, right now, the event is on event 7, okay? Talking about, say, between Obama and Romney during the debate about some US debt problems. And as you look vertically, that you can figure out that people actually can talk about things that have been discussed before or being discussed currently, because we also have the dots below the segment 7, meaning that they actually, at this moment, while the Obama and the Romney were debating about US financial debt problems, we still have the tweets at the moment talk about, at the same moment, talk about the topics that were discussed before. Okay, so which essentially is against this time window-based assumption that all the tweets within this time window should talk about the topics of the event that's in this time window. In fact, we find that's not the case. What's more interesting is that people can also talk about the things which are expected to be discussed later. Okay, and from this insight, what we find is the topic context of the tweets, they did not always correlated with the timeline of the events. An event segment can be referred by a specific tweet at any time, irrespective of whether it has been already occurred or is being occurring currently or will be discussed later. Okay. So that's for the alignment task. And next, we want to talk about what is the second task, which is to infer the event sentiments expressed from the people's tweets or from the people's social media posts. So again, given event like the presidential debate between Obama and Romney or any event, and given the transcript of the event and the tweet about this event, what we want to do in this task is we want to infer the sentiments elicited by the segments and topics of the event on Twitter. We want to know, given the topic about healthcare during the debate, what's the people's opinion about this topic? Like people may say, I like Obama's proposition on this topic versus I do not like Romney's propositions on this topic. So we want to know the sentiment orientations on this task. So what is the problems? So the formal problem definition is like this. Given an event transcript S and its associated tweet T, we want to find the aggregated sentiment, whether they're positive or negative, about the segments and topics of the event that's expressed on Twitter. Okay. And as we all know, that sentiment analysis has been a very classic problem. A lot of research has been devoted into these problems. And a popular solution to solve these problems, and also many existing work to solve this problem, is based on 3 steps. The first step is to manually label tweets with their sentiment orientations as the training data. And then the second step is to apply some off-the-shelf sentiment classifiers, such as Mincut, proposed by Bopon in 2002, to infer the sentiments of the event, sentiments of the tweets. And as the last step, we relate the aggregated Twitter sentiment to the segments and the topics of the event that occur within the fixed time window around the tweet's timestamps. Okay, as an example of this very kind of classic approach, that I took a screenshot of the work done by Nick Dugopoulos and David Sharma on categorizing the debate performance via the aggregated Twitter sentiments. So they use this exact approach to infer the sentiments of tweets expressed against the different segments of the event along the event timelines. And as you can see, that they apply their model. So they consider the degrees of the sentiment. So the more negative means that the people are more negative about the performance of the debater here, which is McCain. And they also did a follow-up work, which is trying to build a web interface in their 2010 advanced work to build a system called the Diamond to analyze different events. So again, the sentiment here is based on this classic 3-step approach. Label the tweet sentiment, apply existing classifier to learn the sentiments, and relate the sentiments to the event segments based on time windows. But is this approach sufficient to our scenario? The answer is not really. Because this classic 3-step approach suffers several limitations. The first limitation is that it's difficult to relate Twitter sentiment to segments and topics of the event. As I discussed earlier, that the time window-based approach sometimes do not work very well. And the second limitation of this approach, this classic 3-step approach, is that manually annotating sentiments of tweets is time-consuming and error-prone. We all know that the supervised learning approaches, they often suffer this problem, that labeling data is very time-consuming, very costly, and error-prone. And the third one is that the Twitter sentiment or any social media sentiment, they are conveyed with highly domain-specific context clues. So because Twitter are very informal English or very informal language, that people can use different expressions to express the sentiment very, very differently. So using the trained labeled data, they are unable to generalize the performance to handle tweets for different events, which essentially or potentially will cost the performance of the models, and the model will become very stale. So in order to overcome these limitations, what we propose is a very flexible event sentiment analysis tool called SOCSENT. So SOCSENT essentially is a matrix factorization framework which incorporates or leverages prior knowledge to overcome these limitations or the challenges. So we use ETLDA to, as a prior knowledge to align the tweets to the event. And we use some domain-specific sentiment lexicon to overcome the third challenge, which is a model style challenge. And we only require, in this model, we only require a few labels for a small set of tweets. So essentially, SOCSENT can be viewed as a semi-supervised learning approach. Okay, And we incorporate this prior knowledge, 3 prior knowledge, into a matrix factorization framework to learn the factors in latent dimensions, 3 latent dimensions: the segments, the topics, and the sentiments. So let's look at the conceptual model of SOCSENT. So SOCSENT is, as I said, it's a matrix factorization framework. So the input to SOCSENT is a tweet term matrix. And we factorize it into 4 parts: the tweet segment, segment topic, topic sentiments, and the term sentiment. Okay? So we want to factorize it into 4 submatrix along 3 latent dimensions. And in the same time, it also requires the factor to respect the prior knowledge to the extent as possible. So we have 3 prior knowledge here. The first prior knowledge comes from the tweet alignment result from ETLDA. So ETLDA essentially gives us the tweet segment alignment. And it will regularize the first submatrix. And the last prior knowledge is the term sentiment matrix. Essentially, we build this matrix from some sentiment lexicon such as MPQA. And if you multiply these 3 factors together, the tweet segment, segment topic, and topic sentiment, these 3 matrices together, you will get a tweet sentiment matrix. And to regularize this, we obtained a few tweets labeled by the graduate students in our department and treated that as a prior knowledge to regularize these 3 matrices. So what does this prior knowledge do? So I'll give you an example, is that assuming that there is a very long integer number that I want you to factorize this long integer number into 4 parts without any restriction or prior knowledge that you can factorize it into a random way. And right now, I give you restrictions saying that the first factor should be between 1 to 10, and the second factor should be between 100 to 150, and so on and so forth. Given this prior knowledge that you cannot, restrictions, you cannot factorize this long integer number into a random way. So you have to follow the rules. So these 3 prior knowledge essentially are the rules that the factorization process should respect. So we model this factorization process as a optimization problems, and we want to minimize the reconstruction errors. And we denote the prior knowledge G0, R0, and F0 here to regularize G, T, S, and F. So let's look at in details what are the content or what's going on in this prior knowledge. So from the ETLDA, we essentially learn the alignment between the tweets and the segments. And so for G0, essentially, we show each row represents a tweet, and each column represents a segment of the event. And the value here represents the probability that this tweet refers to this segment returned by the ETLDA. And on the other hand, for the other 2 prior knowledge, F0 and R0, F0 is on the term sentiment, and we obtain the F0 ground truth or the prior knowledge from MPQA, which is a standard sentiment lexicon. Okay, so each row here again represents a tweet, and each column represents two sentiments, positive and negative. So if this term in MPQA is about a positive, then we make 1, 0. Or if this term is labeled as negative, we make it as 0, 1, and so on. Okay, and the last, for the 3rd prior knowledge, which is the tweet sentiment prior knowledge, we ask people to label sentiment from very few tweets instead of in the supervised learning for a lot of tweets. Essentially here, for this semi-supervised learning, literally, we ask people to only label a few tweets, say less than 1,000 tweets, for the purpose of capturing some domain-specific connotations. So again, each tweet here, each row in this matrix is again represent a tweet, and each column here represents the sentiment of the tweet, either 1 or 0. 1 means the positive, and 0 means negative, and so on. And to solve the optimization problems in SOCSENT, again, this problem is due to the coupling of the parameters, and also this problem is non-convex. So we adopt an alternating optimization scheme proposed by Christine in his KDD paper, and we derive the multiplicative update rules on the left-hand side, and we update each parameters of our models until the model gets converged. To evaluate the SOCSENT, okay, we perform the SOCSENT for a few tasks, such as classification of performance of the sentiment of event segments, and also event topics. And we compare that against some ground truths and some baselines. And the data we use, again, is the President Obama's speech on Middle East, and also the presidential debate called the Denver debate. And 3 baselines are implemented. One is called a lex ratio, which is a lexicon-based approach, and also use the MinCat. And also we use MFLK proposed by Tolly in his ACL paper in 2009, which essentially is a very similar matrix factorization model. And what we find here is that in terms of the classification accuracy, that the SOCSENT improves the approaches from 7% to 18%. And for the classification of event topics, SOCSENT again outperformed these baseline models with a range of 6% to 17%. And we also test the effectiveness of the prior knowledge, because SOCSENT relies on the prior knowledge during its factorization process. We also evaluate the effectiveness of these 3 prior knowledge. So we did a combination of these 3 prior knowledge and look at the performance of SOCSENT on these 3 tasks. And we in general find that combining all 3 parameters, also 3 prior knowledge, achieves the best performance. Okay, so that's the second part which is inferring the sentiment of the event based on the time window based approach, and also some more advanced approach. So for the next part, I'm going to talk about how to identify events from social media, which is an extremely hot topic in recent days. So there are essentially 2 lines of research here. The first one is event detection from social media. The other is event extraction from social media. So let me first talk about event detections. So event detection, as we all know, it's very important and very useful, because as the user said, that many events right now are reported on Twitter. Sometimes they are faster, sometimes they are slower, but many people, since they are people right now can be seen as the social human sensors, they often report what's going on during the event themes, which can serve very important information for the governments, for the journalists, and so on. So the goal of event detection from social media is to discover the new or previously unidentified events, where each event refers to a specific thing that happens at a specific time and a place. Okay, and there are a wide range of event detections algorithms proposed over the past few years, and they can roughly organized by different perspectives. If we look from the perspective of event types, most existing event detection algorithms can be categorized into handling unspecified events versus specified events. So if we look at from the perspective of detection task or the target application, we can categorize the existing algorithm, event detection algorithm, into RED, which is the retrospective event detection, or new ED, which is new event detection. And last, by detection algorithm or methods, we can categorize the existing approaches into supervised versus unsupervised approach, or a combination of both. So here is a quadratic kind of categorization of existing event detection approaches. So we have an unknown approach for the unknown events or unspecified events. We have approaches such as Twitter new event detection, published in NAACL in 2010, and for new events. For the unknown or specified retrospective events, we also have work on event detection on flickers. People did that. And for the known events, for the known new events, so this is a very seminal work proposed by Sakaki, as also you highlighted, is for detecting the earthquakes using Twitter. Why we call it known events? Because we know that, so this type of algorithms dependent on specific keywords to track the events. So they know what kind of keywords that they should track. On the other hand, for the unknown events, we do not know what will happen. So that's why we call it unknown events. And the last part is for the specified known events, and for the retrospective perspective. There's a work from Kennedy and Monaman in 2009 about organizing YouTube concert videos based on their event types. So in this tutorial, I focus on a very kind of popular event detection category, which is to detect unspecified, unknown events in real time. Okay, so this is the unspecified event detection. So what are the challenges in this task? Because as I said, I would say more than 75% of the proposed event detection algorithms falls into this category. Okay, so what is the challenge in this specific task? The first challenge is that because it's unspecified event detection, there's no event information that's available to us. So we do not know when the event will happen. We also don't know what types of the event, and we also don't know what topics of the event. Okay, and since we are trying to detect events from social media, and we all know that social media, especially tweets, they are very brief and with very low quality, meaning that the language on Twitter, they use a lot of abbreviations, unconventional language, and with typos and grammarly not correct. And also, they are very noisy, as you can imagine, that tweets covers different topics, and not all of them related to events. So here is an example that I take a screenshot of the Twitter event, trending event panels on Twitter. And as you can see that in this red box, these are the so-called trending keywords or trending events happening on Twitter in New York City. And it's very hard to make sense of them, right? What is the TGIF? What is CSI? What is PEP? Okay, so TGIF might be easier, but the other two are pretty hard. And on the other hand, although we have a detected event, but they are very, very useless, such as morning Twitter, Friday, and good mornings. So they are not very newsworthy or not informative compared to the event that we want. So how do we solve this problem? How do we identify in real time those unspecified, newsworthy, or high valuable events? So that's the problems for the event detection algorithms. So one particular work I want to mention here, a very classical work, is by Hila Becker, Monaman, and Luis Gravo, published in ICWSM in 2011, on identify the unknown, unspecified events and its associated social media documents, essentially tweets. And it involves 3 steps, and I would say that all the existing, or near the majority of the existing event detection algorithms all have these 3 steps. The first one is to organize the content, extract the features. And the second one is to group the features together into event clusters using clustering. And the third step is to label or to infer whether this cluster is about event or not. Okay. So let's look at some kind of conceptual model of event detection algorithm or event detection workflow. And as I said, the majority of existing event detection algorithms are like this. So given a social media documents like tweets, and the first step for event detection, for existing event detection algorithm, is to do a clustering. So they obtain a clusters, using supervised or unsupervised clustering algorithms. They can get event clusters. They can get clusters. Okay. And next, they need to infer whether these clusters are newsworthy or about event or not. So in this step, they run a classification task to infer the label of the clusters to see whether they are about the news or not. So as a result, they will get a clusters and they will infer the labels of the clusters, and the result of this classification, they can infer, okay, these clusters are about event or not. Then they can apply some summarization tools to summarize the event. So this is, in general, a workflow for event detections. First, build a representation of documents. Second, do a clustering of the documents. And the third step, do a classification of the clusters to infer whether a cluster is about event or not. Okay. So for the first step, a basic approach here, and also in their work, is to order tweets by their post time, by timestamps, and they use TF-IDF vectors to represent the textual content of the event. And they can get other features from Twitter to augment this feature vector. And as a second step, as I said, they need to do a clustering. And there are many alternative clusterings available. And a very popular choice is so-called single-pass incremental clustering algorithm, which is very scalable, it's online fashion, and very, very effective for identify the events in text news. And for this kind of algorithms, a common requirement is that people do not want the clustering algorithm to specify the number of clusters in a priori, because we do not know how many events will happen. So it's very hard to determine the number of clusters here. Okay. Okay. And so here is the cluster-based approach that's used in this very classic paper by Hila and Mon and Ruiz, that they group the tweets based on the online clustering, and they compute the statistics of the cluster content, such as the top terms, number of documents per hour, and so on. And they set up a certain threshold to see whether this is a trending event or not. And once we finish the clustering phase or the clustering algorithm, the next step is to apply a event classification or classifier to determine whether the cluster is about news, about event or not. So essentially, this is a very classic classification task, which requires the training data and the feature extractions. So for features, they extract the several features, the social interaction features, such as retweet and replies in a cluster, and they extract the topics from clusters, and they also look at whether the cluster has the trending behaviors by comparing the standard derivations from expected values, expected volumes. And they also look at the Twitter-centric features such as tagging behaviors, the hashtags in the cluster. And they use these features to build a classifier. And in their paper, they use the SVM and use the human annotated training data. But the other classification model can also be work, such as real-time, one versus all, or one versus any. Okay. And here is the evaluation of the performance of their event detectors by this work. And in general, they find that they can achieve very high precision and recall. And I also put some kind of sample events identified there by their classifiers. Okay. And the last part I would talk about, it's also very interesting, is called event extractions. So what is event extraction? So event extraction is to extract a structured representation of events, and which is kind of different from event detection. And recall what we say event detection is trying to discover raw or previously identified events where each of the events refers to a specific scene that happens at a time and a place. So the event extraction is more about information extraction of the events from the social media post rather than detecting a trending event from the social media post. Okay, so that's two different goals. And for the event extractions, a typical goal here, a typical approach here is that they want to extract, given a tweet, a given social media post, they want to extract which set of events that they want to know about, and how soon they can know about an event. Okay, and I want to talk about a particular example, a very classic example about event extractions. So this is done by Alan Reeder, Mawson, and Oren Cheney, and Sam Clark, published in KDD 2012 about open domain extractions from Twitter. So, so this is a screenshot of their demos. So what they did is they applied event extractions to on Twitter to build a event calendar. Okay, so you have an event calendar here, and if you click one of the entry about in a calendar, you can look at what tweets are about this event, or extract it automatically using their approach. And also you can look at the significance or how many people are talking about this event. So this is one about the Lenovo product. They extract the keywords such as start ads, start, and Ultrabook available. Essentially, this is an event about Lenovo releasing its Ultrabook in this press conference. And these are the tweets about this event. So in order to do the event extractions, and there are several kind of standard steps. The first step is to do the POS tagging, the part of speech tagging of the events. And the second step is to extract the named entities and the event phrases, and also to resolve the temporal expressions and categorize the extracted events into types. And the third step and the last step is to measure the significance or the strength of the association between the extracted events and the time that they occur in order to determine whether this event is significant or not. And this is important, as I said in the previous examples, that the Twitter event detection algorithm can show something like morning Fridays, which is not very important compared to what we actually want. So doing the event extractions are not very simple because, again, thanks to the informal aspect of the social media posts. And there are a lot of unreliable categorizations, a very unique grammar, and lexicon variations that impose a lot of challenges for doing the event extractions or extracting the named entities from tweets. And applying the existing off-the-shelf NLP tools often fail because of these challenges. So in order to do this, these authors, Alan Reeder, Mawson, Oren Cheney, and Sam Clark, they propose a new Twitter-based POS tagging tools. And so what they want to do is they want to extract the event phrases, such as Apple to announce the iPhone 5 on certain day, October 4th. Okay, so in order to do this, they first annotate the tweets, and then they run the sequential label tagger, such as the conditional random field, to infer the tags of the words on the tweets. And they use a bunch of features in training their conditional random fields, such as the PS tags, adjacent words, directory features, and other features such as the prefix and suffix. And at the first step of their event tagging, their event taggers can achieve very good performance in terms of the precision and the recall compared to some of the baselines. And at the next step, they need to categorize the event types. So they need to know what type of the event is, whether it is about sports, whether it is about politics, or a product release. Okay. So in order to do this, essentially, again, this can be viewed as a classification task. But it involves a lot of challenges, such as there are a lot of different types and open domain types, and not sure which is the right set of types because it's hard to predefine, and the types may change. So what they do in order to handle this challenge is they propose latent variable models such as this. So each variable here, so the theta here represents the event phrase that's modeled by a mixture of types. And each event type is associated with a distribution over named entities, the extracted named entities and the dates. And by using this generative model, they are able to infer the types of the events. And I will skip the details, but showing some kind of example of the labels or the types of the events that they extracted, and also the entities and event phrases associated with these types of the event. For example, for sports, we have the entities such as ESPN, NCAA, Tigers, and Eagles, and so on. And the event phrases are about tailgate, homecoming, regular season, and so on and so forth. Okay? And so I will skip this. And the last step in their approach is to rank the event, because there are so many events and they only have a few space to show this event. So in order to determine the significance rather than the frequency of the events, they use some statistical significance tests, such as the p-values, chi-squares, to compute the association between events and the dates of the event. And they conduct end-to-end evaluations to evaluate their whole system, and the performance of their approach is significantly better than the baseline approach. They can achieve more than around 90% of the precision. To summarize of my part is that there are two problems people researched extensively. The first problem is to categorize the event using social media, and two subtasks people are done in the past is to first establish the alignment between events and tweets, and second is to infer the sentiment of the tweets expressed against the event topics and segments. And we also talk about some event detection algorithms and event extraction algorithms. And for the futures, a lot of research right now extend that for instead of doing the research or using the data from textual data, a lot of research have been done for multimedia. And as we will see in the second part, Jiebo is the pioneer in this space to do a lot of analysis using not just the textual data, but also the imagery data. And the other very active line of research is to improve the accuracy of the proposed models. And I will stop here, and I'd like to take any questions if you have. Any questions? Yeah. Thank you.